Welcome and hello. This is a video lesson in HY-8, and what we're going to be talking about in this lesson is the alternative designs feature built into the crossing data dialog box. All right, so let's go ahead and get started. What I have on the screen is my crossing data dialog box for crossing 1. I'm going to close that and open it back up by just going up to edit the culvert crossing data. Boom, here we are. The alternative design button is right over here in the top right section of this dialog box. The alternative design feature assists modelers to determine the optimal culvert size while complying with specified design requirements. The details for this feature are covered in section 4.8, chapter 4, section 8 of the user's manual that begins on page 61. Before we can use the alternative design feature, we need to fill out our crossing data, our crossing properties over on here on the left half of the dialog box, as well as our culvert data and site data. The user manual also mentions that certain data is not required or would preclude the use of the alternative designs. Specifically, you can only have one culvert here. You can't have multiple culverts, but you can have multiple barrels. We'll talk about that once we get into the designer. And then a few other things. You cannot use depressed inlets. So depressed inlets, I have that set to no. If I happen to have it set to yes, for instance, let me change it to yes. And then I click on alternative designs. Boom, it gives me this error message. The alternative designs module does not function with inlet depression. So I need to change that back from a yes to a no. Okay. Also, the alternative designs will not work if we have a culvert type that has tapered or has a broken back. So I'm just going to keep my culvert type at simple. All right, so once that's done and your culvert data is ready to go with all your roadway data and site data and so on, go ahead and click on this alternative design button. It'll bring up this dialog box right here. Now what we're doing is inputting the data for the shape alternative, culvert design options, and design requirements. Once all that's set and ready to go, come down here to the bottom right corner and click on this determine design alternatives. That's basically the calculate button. Then the calculations will run and then we'll see the results. Now this dialog box cannot be resized and is annoyingly tall. So I'll just zoom in on the top half of the dialog box here. All right, so the shape alternatives, this lists all the shapes as well as all of the materials for each shape. So right now I only have the circular shape, the circular shaped culvert selected. And then if I click the plus to expand, I see the different materials that are allowed for that particular shape. Now I can go ahead and toggle them on or toggle them off. Since this is the first time I've used this feature on a video, I'm going to keep things simple and only use circular and concrete. If you click on concrete, as you see, we have different options here for the different inlet configurations. So I'm, again, just going to keep these simple and go with the top option of square edge with head wall, as opposed to using all of the options. Okay, so that can get pretty carried away with all of the shapes, materials, and inlet configurations, but we're going to keep it simple and just go with circular, concrete, and this inlet configuration. All right, so I'm going to collapse these out, but here we have concrete and the different inlet types there. We have elliptical, the different materials, the different inlet types. Yeah. All right, so over on the right half of this dialog box, we have the culvert design options. This section allows you to define parameters and preferences that will guide the design process. So the first one here is span to rise ratio when applicable. The default value here is 2. That basically means that the span or the width is twice the rise or the height. So this would be applicable for shapes with 2 dimensions but without predefined geometry. So that would refer to the concrete box and the South Dakota concrete box culvert. Most of these other shapes here have predefined geometry that you would select from a table. So for circular, what I'm doing here with circular, that will not apply because circular only has one dimension, i.e. the diameter. The diameter in this case would also serve as the rise. Okay, the next one down is rise increment when applicable. When applicable here means that the rise applies to shapes with one dimension. So this does apply for circular. It has the one dimension, which is the diameter, which is the rise. and it tells HY-8 how much to change that dimension when testing the next size up. So it's going to start with a small size and then increment by this rise increment right here. So we'll just say 0.5 feet. So it'll start at half a foot diameter, 1 foot diameter, 1.5 foot diameter, and so on up until it finds its solution, if there is a solution. The next field down here is the number of barrels. So if I put a 1 here, it's only going to try to convey that flow through the culvert at that just for 1 barrel. If there's 2 barrels, it'll be able to convey more flow, 3 barrels, even more flow. And if there is a solution, then the number of barrels will be inversely proportional to the design size that it finds when running the computations. All right, the next field down here is minimum cover. So I have it set to 2 feet. This is the minimum vertical distance between the top of the culvert and the roadway elevation. So the roadway elevation I have over here, crest elevation of 170. Let me go ahead and close this. In that elevation right here of 156, subtracted from 170 is 14 feet, plus the additional 2 feet of cover means that the largest diameter pipe that I can test would be 12 feet. All right, so you sometimes need to look at the data that you have here for your site data and your roadway data, and that will influence the constraints on this design, especially considering the minimum cover right here. All right, the next section down here is our design requirements. So this is the section where we specify design criteria, such as the constraints that govern what is considered an acceptable design. So we're going to start off by selecting our discharge here. This is our design flow. The list of discharges in this table come from what we define as our discharges over here for our crossing properties discharge data. So these are the user-defined discharge values that I provided. Let's go ahead and set that at the maximum of 800, and that's in units of CFS. Below that, we have a drop-down here for design criteria, and then our options are lower than the given freeboard of the roadway, and then we type in what that freeboard is in feet. The other option is lower than a given headwater elevation, and then we type in what is that headwater elevation. So for headwater elevation, for instance, the crown elevation of the roadway is 170 feet. So if I wanted there to be, say, 2 feet of clearance, I would type in 168 right here. So the maximum headwater elevation can come up to 168, which is 2 feet below the roadway crown elevation. However, if I wanted to use the other option, which is lower than given freeboard of the roadway, I could type in like a 2 right here, and that would be 2 feet below the roadway, 2 feet of freeboard. The next 3 options in design requirements are optional because you can toggle them off using these checkboxes. The first one is maximum headwater divided by D. What that is it limits the depth the water is allowed to back up. So HW is the depth of the headwater, and then D is the rise. So for a circular pipe, the rise is the diameter, but for, say, a concrete box, the rise would be that vertical opening, the rise, the vertical opening of that culvert, the dimensions. The user manual says that 3 is the recommended maximum, but of course that sort of depends on which selected discharge you choose here. So by 3, that basically means that the headwater cannot exceed 3 times the diameter that is selected in the design. And we'll see when it's computing that that particular diameter is going to be increasing with each iteration, in which case the maximum headwater will also be changing because that rise will be changing. Okay. The next one down is similar, but sort of the opposite in concept. It is the minimum HW/D ratio. This prevents HY-8 from selecting oversized culverts that barely get submerged. It ensures that the culvert is used efficiently. They mentioned to use 0.5 as the recommended minimum, but again, that sort of depends on what you're actually trying to calculate and compute based on the specific flow rate that you select. The last design requirement is this last one here. Outlet cannot be submerged. Just like it says, if you have this checked on, then the design cannot submerge the outlet. All right, so you can check these on or check them off. I'm going to leave them checked off. And now we're ready to do an example. So I'm going to just run this example right here. So what we have is a design flow rate of 800 CFS. We're constraining it to just one barrel. We have the minimum cover of 2 feet. And then we're going to come down here to the bottom and click on this Determine Design Alternatives. And when I click that, we'll see the message box pop up and see the calculations take place. Towards the bottom, I see this message that says HY-8 found the smallest culvert that fulfills the requirements. And it looks like that took place at a culvert rise of 9.5. So that'd be 9.5 feet. You can see it's counting up the different trials and the different computations and the diameter of that barrel size, or the culvert rise is what it's called. Okay, so I'm going to go ahead and click close. And when I do, it pops up these results right here. There's only one result because we only specified one shape and one material and one inlet configuration right here. That is the first 3 columns of the table. And then further over, we have some other data, such as the span and the diameter. Of course, since this is circular, it's the same number, the number of barrels, the design flow rate, and then a few other hydraulic parameters listed over here. Okay, I'm going to go ahead and close that. What I'm going to do now is increase the number of barrels. So I'm going to click on Alternative Designs. And then for max number of barrels, I'm going to change the 1 to a 2. That's the only change I'm going to make. Not going to mess with any of the other parameters. I'm going to click on Determine Design Alternatives, which is basically the compute button. It found the solution for 1 barrel, and then it found the solution for 2 barrels. It says the calculation took 3 seconds. And now if I click close, I now have a row in the table for each of my solutions. The first row is for 1 barrel. The second solution is for 2 barrels. And notably, the 2-barrel solution has a smaller diameter. Okay, let's do that one more time for 3 barrels, and then we'll talk about exporting these results. So back to the alternative design, I'm going to change the 2 to a 3 and then click compute. So it's running through the first barrel, now the second barrel solutions, now the third barrel solutions. Okay, I'm going to click close. Now we have 3 solutions for barrels 1, 2, and 3. If we have 3 of those circular barrels, the diameter is 5 feet. And just out of curiosity, we're increasing the rise by 0.5 feet. But if I change it to something smaller, like 0.1 feet, I'm not saying that's possible, but just as far as the mathematics goes, we know that 1 barrel will actually be between 9.1 and 9.5 feet. 2 barrels will be between 5.6 and 6.0, and then 3 barrels will actually result in 4.6 to 5.0. Okay, let's go ahead and make that change. So I am going to change the 0.5 to a 0.1, and then click on the Determine Design Alternatives button. This computation may take a little bit longer simply because it's checking 5 times as many results. This is not a very efficient search, but it's doing it this way anyway. Okay, 4.8 for the 3-barrel solution. Let's go ahead and check out our numbers. So 9.1, that was much less than 9.05. 6.0, that's the same, and then 4.8. So that's the difference between using a 0.5 foot rise discretization and a 0.1 foot rise discretization. All right, as for exporting the results, we can click the checkbox in this far left column and then click on this Export Selected Crossings. So it will export across each of these crossings into a .HY-8 file. I'll do that to demonstrate. So click on Export Selected Crossings. Here's my desktop. I'll just call this file1.hy8 and then click Save. When I do that, I'll have a .hy8 file that popped up onto my desktop. We're going to open that up in just a little bit, but before we do, I want to demonstrate how to update selected crossings. You can also toggle on or toggle off all of the checkboxes using this button right here, Toggle All Rows. What I'm going to do is select just one row. How about the second row with 2 barrels? And when you have only one of these checkboxes checked on, this button for Update to Selected Crossing becomes enabled. So when I click that, what it's going to do is it's going to change the number of barrels and the diameter in my culvert crossing data to what I set it to. So right now the diameter is 4 and the number of barrels is 1. And there may be some other updates that take place, but let's just go ahead and click the button and confirm that that works. Update to selected crossing. Okay, so that closed and boom, here is the diameter of 6 feet. And then here is the number of barrels, which is 2. All right, so one last thing before we finish up, let's check to see this data. that's saved in that exported .hy-8 file. I'm going to click OK and then click Save. Then I'm going to click on Open, navigate to my desktop. Okay, I'm already there. So I'll open up that file. Now what I'm seeing is 3 more crossings that have been added. They're all called Crossing 1, and Crossing 1. They're all called Culvert 1, Culvert 1, and Culvert 1. You may have noticed as I just clicked on them, the profile view that we're looking at right here. Is that what it's called? Views. Okay, it's called side view here in HY-8, but side view, profile view. Culvert 1 right here, this is the single barrel solution with the largest diameter. See, we have like, what was it, 9 feet right here. And then Culvert 1 again, this is the 2-barrel solution. I should probably call it 2-barrel solution or something besides Crossing 1 and Culvert 1 every single time. This is the 2-barrel solution. This is the one we added in. And then the last one here is the 3-barrel solution. It has the smallest diameter. They're all using the same design flow rate of 800 CFS, so that's good to see. Now let's go ahead and check out the data. So let's look at the 3 culvert solution. I can just right click and open up the culvert crossing data. And what we have is 3 barrels down here. We have our diameter of 4.8 feet right here. And then all the other data that was saved was successfully exported to this crossing data. So all of the crossing properties and the culvert data and site data have been preserved. All right, well, that was it for this lesson. What we talked about was the alternative designs feature in HY-8.